Welcome everyone to today's FTCOE webinar evaluating a statistical method for comparison of mass spectra of novel psychoactive substance. Our presenters today are Professors Ruth Smith and Victoria McGuffin, both with the Department of Chemistry at the Michigan State University. So without further delay, I'll go ahead and turn things over to Dr. Smith. Thank you.
Good afternoon, everyone, and thank you for the introduction, and thank you everyone for joining the webinar this afternoon. And today I'm going to spend some time talking about a method that we've developed in our lab that allows the statistical comparison of two mass spectra. Now, in theory, this method could be applied to any two mass spectra, but in the last several years, we've really focused this method on applying it for the association and discrimination of novel psychoactive substances, and with real focus on distinguishing structural and positional isomers. So before I start, I want to acknowledge the National Institute of Justice who have funded this work over many years. So back in 2008, there was an initial award to develop the method. And then in 2015, another award to really demonstrate initial applications of the method for seized drug identification. And then more recently, an award in 2020 to evaluate the robustness and the ruggedness of the method. And most of the data that I'll talk about today came from the award from 2020. So I'm sure many of you are familiar with this sort of workflow in seized drug identification, where a sample is submitted to the lab, analysed by GCMS, and generating the electron-ionization spectrum of that sample. And for identification purposes, the spectrum of the submitted sample is compared to a spectrum of either a reference material analysed under equivalent conditions as the submitted sample, or it's compared to a spectral library. And the next few slides, I just want to highlight a couple of challenges with these comparisons of submitted sample spectra to these reference spectra. So here is an example of what I'll call my submitted sample. So it's a spectrum that we generated in the lab, and we also analysed a Utalone reference standard at the same time. So comparing these two spectra, you can see that there are certainly some similarities, but there are also some differences. So for example, neither of these spectra contains the molecular ion, which would be expected at around mass to charge 235. Both spectra have the base peak at mass to charge 86, and both spectra have similar dominant ions present. So for example, mass to charge 58, 71, 121, and 149. Now, some of the ratios of these ions are similar. So for example, mass to charge 121 and 149 are similar in the reference and the submitted sample spectra, but the ratios of mass to charge 58 and 71 are different. So 58 is lower intensity in the submitted sample, but higher intensity in the reference standard. So while there are these visual similarities, there are some differences that might preclude an identification being made just based on this visual comparison. This next slide shows the comparison of the sample spectrum to library databases. So the screenshot at the top right there shows comparison to the NIS17 library, which is the library present on our instrument. The top hit here is BKDMBDB, which is a synonym for dibutylone, but the quality match is only 83. The second top hit is Utalone with a quality match of only 72. So taking the same spectrum and comparing it to the Swig drug library, this is the Swig drug 3.12 version of the library, and this time the top hit is dibutylone, but a quality match of only 83. So in terms of this identification, it's really difficult to do this just based on the visual comparison of spectra, whether it's to that reference standard or whether it's to a library database, because the spectra have these similarities, they have these differences. The library is indicating potential match to dibutylone, but the quality match factor is not necessarily that high, and therefore an identification might not be possible without doing additional work. So this submitted sample was actually a spectrum of dibutylone. And given dibutylone and Utalone are structural isomers, obviously these spectra are really, really similar. And this is really the starting point for us in developing our method, because we wanted to have a method by which we could compare two mass spectra, so the submitted sample to that reference spectrum. And we wanted it to be a direct comparison of the two spectra, but also moving away from the visual comparison and having a method where we could have a more objective comparison that allowed statistical confidence in the identification. Now, the main point I want to make here is to highlight that the method that we've developed is not a search algorithm. This is really a method to be done to compare the two spectra, the reference spectrum and the submitted sample. So the method that we developed is based on the unequal variance t-test, and we perform that to compare the intensity of corresponding ions in the two spectra that are being compared. So for each comparison, we're testing the null hypothesis that the difference in intensity is equal to 0. And that would indicate that there's no statistically significant difference in intensity of that ion in the two spectra. In contrast, the alternative hypothesis is that the difference in intensity is not equal to 0. So that would indicate that there's now a statistically significant difference in intensity of that ion between the two spectra. So this slide just shows the calculations that are being done for these comparisons. So it's the unequal variance form of the t-test. So this is the equation for the calculated t-value, where we're taking into account the mean intensity of the ion in spectrum 1 and the mean intensity of the ion in spectrum 2. And we're also taking into account the variance associated with the ion intensity. The equation shown in the middle is for degrees of freedom. So this is the unequal variance form of the t-test, and we have to calculate degrees of freedom using this equation here, which also takes into account the variance associated with the intensity. So the degrees of freedom, along with the confidence level at which we perform the comparison, are used to generate the critical t-value, and the calculated t-value is then compared to that critical value. If the calculated value is less than or equal to the critical value, then we accept the null hypothesis, and that indicates again that there's no statistically significant difference in intensity of that ion between the two spectra. In contrast, if the calculated value is greater than the critical value, then we don't accept that null hypothesis, and that would indicate that there's a statistically significant difference in intensity of the ion. So to perform this method for two spectra, we basically compare each ion in the scan range. So in these two spectra that I'm showing on the slide here, the scan range begins at mass to charge 40. So we compare the intensity of mass to charge 40 in the sample compared to mass to charge 40 in the reference spectrum, and we perform the t-test to evaluate whether we're accepting or not accepting the null hypothesis. And then we move on to mass to charge 41, and we do the same comparison, determining if the null hypothesis is accepted or not accepted. And we do that for all ions in the scan range. So obviously that's a lot of t-tests and a lot of calculations that are being performed. And so we've automated this in the form of an Excel spreadsheet. So this spreadsheet is set up with all of the calculations. There's a series of logical functions in here that automatically perform the calculation of the t-statistic, the degrees of freedom, generates the critical value, and compares the calculated and critical values. So an analyst in a lab who is using this method is basically taking the mass spectral data from the instrument and pasting it into this Excel spreadsheet. So the version of the spreadsheet that I'm showing here allows you to compare triplicate spectra of spectrum 1, in this example a case sample, versus triplicate spectra of spectrum 2, in this example a reference standard. Now, to this point, most of our work has been done using Agilent GCMS systems, and they're older systems that use ChemStation software. And in ChemStation, there's a function by which you can tabulate the mass spectral data, and you can basically copy that and then paste it into the Excel spreadsheet. So any instrument software that you have the ability to export the mass spectral data like that, you can use this comparison method. So an analyst would paste in the mass spectral data for the spectra that they want to compare, and also over here set the confidence level at which they want to perform the comparison. As I said, all of the calculations and comparisons are then automated, and the results of the comparison are returned in this output box shown at the top of the screen here. Now, I'll come back and talk about that in just a second, but I want to show another part of the spreadsheet where essentially all of the calculations are being performed. So once the mass spectral data are pasted in, the spectra are automatically zero-filled. The mean intensity and the standard deviation associated with each ion in the two spectra being compared are populated. The t-value is automatically calculated, so the column that's labeled t-calc is filled with the equation for that t-statistic calculation, so that's automatically performed. The next few, let me put my laser pointer on. The next few columns here are showing or calculating the numerator and the denominator for the degrees of freedom calculation. And the actual value for the degrees of freedom is input in this column here labeled DOF. Then the calculated value is compared to the critical value, which is automatically populated based on the degrees of freedom calculation and the confidence level that the analyst has selected. And then the final column over here that's labeled stat-diff is where we're actually doing that comparison of the calculated and critical t-values. And this column is set up to return a binary output, either a 1 or a 0, depending on whether the null hypothesis is accepted or not accepted. So when the calculated t-value is less than the critical value, we return a 1, which indicates that the null hypothesis is being accepted. And in cases where the calculated t-value is greater than the critical value, we return a 0 here. And that indicates a case where the null hypothesis is not accepted. We then take the product of this column here to basically compare or evaluate all of the mass to charge values that are present. And if this product returns a 0, that indicates that there's at least 1 0 in the scan range, meaning that the null hypothesis has not been accepted. So there's at least one ion for which there's a statistically significant difference in intensity, and therefore the spectra can be distinguished. So if I go back to the output box, which is shown up here, this really just returns a summary of all of those comparisons. So for this particular comparison, the question at the top here is asking, are the samples statistically different? And the answer is yes. And we return the number of discriminating ions. So this is the number of ions for which the null hypothesis is not accepted. Now, if I go just back one slide here, ions for which the null hypothesis is not accepted, we actually flag these in colour over here, and we return the actual mass to charge value of those ions that are responsible for the discrimination. So in this particular example, we have 10 ions for which there's a statistically significant difference in intensity, and therefore the two spectra can be distinguished. So that example was, again, that dibutylone to utylone example. So now we can say that while we can see that there are visual differences, we can now confirm that there are statistically significant differences in intensity, and we can return the number of ions for which those differences are significant, allowing discrimination of these two cathinones. And I'll come back in a little bit and talk more about these particular ions. But I just wanted to show an example of association to show the other side of it. So this is just replacing the dibutylone sample with a utylone sample and comparing to the utylone reference standard. So if we do the statistical comparison, so here I've just pasted in the spectral data for that utylone sample. And now the output box up here is showing that the samples are not statistically different and there are 0 discriminating ions, meaning that the null hypothesis was accepted for all ions in the scan range. So in terms of this comparison, we can now say that these spectra are statistically indistinguishable at this confidence level, and there are no discriminating ions present. So as we started doing this work, once we had developed the method, we then started applying the method to look at association and discrimination of structurally similar compounds. And we worked with sets of amphetamine-type stimulants. We worked with salvinorins extracted from Salvia divinorum. And then around that time, novel psychoactive substances were becoming much more popular, and not only new compounds being identified, but also structural and positional isomers of these compounds. So the next step we wanted to investigate was applying this method to statistically compare structural and positional isomers of novel psychoactive substances. So to do this, we selected synthetic cathinones, fentanyl analogues, and synthetic cannabinoids. And we selected these compounds after looking at a document that's published on the OSAC Seized Drugs Subcommittee website. And this document is called GCMS Analysis Considerations. It's an Excel spreadsheet that basically highlights groups of compounds for which it's known they're difficult to distinguish based on their EI mass spectra. So it's a really nice document, and for many of these sets of compounds, it gives some indication of ions that might be sufficiently different to allow discrimination of the compounds. So we went through that document and we pulled out the cathinones, the fentanyls, and some synthetic cannabinoids that were known to be difficult to distinguish, and those were the ones that we focused on for this part of the work. We then collected spectra of these samples on 2 different instruments over a 12-month period. So one of the instruments was the one in our lab. We had 10 collections over the 12-month period. This is a well-maintained Agilent instrument. And for this work, we had a dedicated column. It was a DB5 column, but we would put that in the instrument, we'd collect the spectra, and then we would take that column out so that the instrument could be used for other applications. And then the second instrument that we used was also an Agilent GCMS system, but it was in one of the teaching labs that we have here at MSU. So this was a more widely used instrument, still a well-maintained instrument, and we did not have a dedicated column in there. So in doing analysis on 2 different instruments, we were trying to just capture inherent instrumental variation that we might expect as we're collecting data on these instruments over time. We also prepared all of these analogues at different concentrations so that we could evaluate the effect of spectral intensity on the ability to associate and discriminate these compounds. And then the ultimate goal was to really identify reliable ions for the discrimination of these very structurally similar compounds. So this slide here shows the cathinone structural isomers that we were interested in. So dibutylone and utylone, I used these to to start the presentation and show examples. So we had both dibutylone and utylone, and we also added propylone and pentalone. Now, in terms of the OSAC Seized Drugs Subcommittee document, they had highlighted 5 ions that might be different among these 4 structural isomers. 2 of the ions were mass to charge 41 and 42. Our scan range here starts at mass to charge 40. So 41 and 42 are really low intensity ions that you can't really see very well. The other 3 ions that they highlighted were mass to charge 44, 58 and 71. So mass to charge 44, you can see that there might be significant or differences in intensity between propylone and pentalone, but we don't know if these are significant differences. And then mass to charge 58 and 71 might allow distinction of dibutylone and utylone, but again, we don't know if these are statistically significant and reliable differences. So this is just a summary of our first spectral collection, where we had all 4 of these cathinones. We auto-tuned the instrument, we performed the spectral collection, and then we did the statistical comparisons. So this table summarizes comparison of dibutylone collected on one day to other spectra of dibutylone collected on a second day. When we did that comparison, we had 0 discriminating ions. So that means that the null hypothesis was accepted for all mass to charge ratios, and therefore these spectra were statistically associated. In comparing dibutylone to utylone, we had 10 discriminating ions, which are listed here. And then comparing dibutylone to propylone, 12 discriminating ions, and dibutylone to pentalone, 14 discriminating ions. So it was relatively easy to discriminate dibutylone from these other 3 synthetic cathinones, with 10 to 14 ions responsible for discrimination. And again, going back to the ions highlighted in the OSAC document, those were 41, 42, 44, 58, and 71. And you can see that these do appear as discriminating ions throughout these pairwise comparisons. So now we can say that, yeah, these ions are important and they're statistically significant. But in addition to these ions, we also see that there are other ions responsible for discrimination. And some of these ions are pretty low intensity ions, so they're not readily visible when you're looking at the spectra. But even though they're low intensity ions, there's still significant differences in intensity that these ions are still really useful for discrimination among these compounds. Now, in another part of the work, we wanted to look at the effect of spectral intensity on the ability to associate and discriminate. So we had these compounds prepared at different concentrations. At the moment, the concentrations we're looking at are 1 mg per mol, 0.5 mg per mol, and 0.1 mg per mol. So we had dibutylone as an example, and that was kept at 1 mg per mol. And then we compared it to the other cathinones where we were varying the concentration from 1 to 0.5 to 0.1 mg per mol. So in this particular collection, when we compare dibutylone to the other 3 cathinones, we have discrimination at the 1 mg per mol level, 24 to 31 ions responsible for discrimination. When we reduce the concentration of one of the compounds and then compare to dibutylone at 1 mg per mol, you can see that we still have discrimination, although we have fewer discriminating ions. So the number of discriminating ions decreases as spectral intensity decreases. And if we lower that concentration further, 0.1 mg per mol, one thing to point out here is this axis is now an order of magnitude less than it was before. It's now times 10 to the 4 rather than 10 to the 5. So this really is a low intensity spectrum. And we can still get discrimination dibutylone of these other 3 cathinones, but there are fewer ions responsible for discrimination. So this, in terms of recommendation, we would say that if anyone was using this method, you would want to make sure that the spectra, the 2 spectra that you're comparing, are similar intensity to have accurate comparisons. The other part of what we wanted to do in this work was to get an evaluation of how much inherent instrumental variation is affecting the ability to associate and discriminate these isomers. So we did spectral collections, a total of 10 spectral collections over that 12-month period. So that was roughly every 6 to 8 weeks we were collecting spectra of these compounds. Before every collection, we would auto-tune the instrument, and then we would collect the spectra over a couple of days and then do the spectral comparison. And then the next month, same thing, auto-tune the instrument, collect the spectra and do the statistical comparisons. So in the table here along the top, C1 to C10 just represents the 10 different spectral collections. So again, if I'm looking at dibutylone compared to itself and then the other 3 cathinones, first of all, dibutylone compared to dibutylone. For 9 out of our 10 collections, we had 0 discriminating ions, so association of corresponding spectra as we might expect. However, there was one collection, collection 5, where we only had 1 discriminating ion. Or we had 1 discriminating ion. So this is actually a false discrimination. We expect spectra of dibutylone to be associated. So when we're doing these comparisons, we had triplicate spectra of spectrum 1, triplicate spectra of spectrum 2 that were being compared. And this discriminating ion was mass to charge 85. So it's a very low intensity ion that was only present in 1 or 2 of the total of 6 spectra that were being compared. So it was a statistically significant ion. However, it wasn't a reliable ion because it only appeared in a few of the spectra that were being compared, and it only appeared as a discriminating ion in this particular collection. In terms of comparison of dibutylone to the other cathinones, we have discrimination in all cases across all collections, but you'll notice that the number of discriminating ions actually varies according to collection. And so to understand this, we started looking at the mass spectral tune conditions. So we're auto-tuning the instrument prior to spectral collection. So we started looking at the auto-tune and some of the auto-tune parameters. So this plot on the top here shows the electron multiplier voltage in the dark green bars and the electron multiplier gain as the orange trend line. And what you can see is across these collections, the electron multiplier voltage doesn't change too much as you might expect, but the multiplier gain does vary quite a bit, from about 1.5 times 10 to the 4 in collection 9 up to about 3.5 times 10 to the 4 in collection 2. So there's quite a bit of variability in the gain here, which is affecting spectral intensity, which in turn is affecting the number of discriminating ions. We also looked at the abundance and the ratios of 3 of the calibration gas ions in the autotune. So mass to charge 69, 219, and 502. So for the first 7 collections, you can see that there's definitely some variability in the abundance of these ions, as you might expect, but the ratios of these ions within a collection remains quite consistent. However, when we got to our later collections, 8, 9, and 10, you can see that these ratios begin to change. So for example, in collection 8, the ratio of 69 to 219 is closer to a 1-to-1 ratio. And in collection 10, mass to charge 69 is actually the most intense of these 3 calibration ions. So this is just a measure of inherent instrument variation. We're not trying to correct for this. We're not trying to standardize for this. We're just trying to capture how much variability could we expect when we're analyzing samples over a longer period of time, and how does that affect association and discrimination. In all cases, we can still discriminate. It's just the number of discriminating ions varies. And so then we started moving toward identifying, okay, which ions are actually reliable for this discrimination, which ions consistently appear as discriminating ions in all of these collections. Now, not only that, but we looked at the spectra that had been collected on a second instrument, where we had also done the spectral comparisons. And then we looked at the discriminating ions there and really just compared which ions do we see as discriminating, not only over time, but on both of these different instruments. So this is summarized in the table here, where I'm showing dibutylone compared to the other 3 catenones. And now these ions here are reliable ions for the discrimination of these catenones over time and on 2 instruments. So for dibutylone to utylone, we have 4 ions responsible for the discrimination. For dibutylone compared to propylone, we have 6 ions. And for dibutylone compared to pentylone, we have 7 ions responsible for that discrimination. Now, again, if I go back to the OSAC document that I mentioned earlier, that document had highlighted 5 ions as potentially useful for discrimination. And these 5 ions are appearing as reliable ions over time and on 2 different instruments. But not only that, we have these additional ions that we can now say are very reliable for discrimination of these cathinones. And again, some of these ions really are low intensity ions, but they're still very reliable for that discrimination. This is just showing utylone to the other 3 cathinones, and same trend observed here, where the ions that the OSAC document highlighted, again, are still seen as discriminating ions, but we have some additional ions present as discriminating ions. And then finally, propylone to the other 3 cathinones, similar trend, that we have a range of ions that we can now consider reliable for discrimination of these structural isomers. Now, the last part of my presentation, I want to move to talk more about positional isomers, because this is really much more challenging than structural isomers. At the moment, we're working with 4 different fentanyl analogues, and we have the ortho, meta, para isomers of each of those 4 analogues. So we've got fluoroisobutyryl fentanyl, or FIBF isomers, which I've got the spectra shown here. We're also looking at the FBF analogues, and the methylfentanyls and the fluoromethoxyacetylfentanyls. But same idea here, we're collecting spectra of these positional isomers over time. I think we've got 7 collections of these isomers. So we're looking at these isomers over time and on 2 different instruments to evaluate, again, association and discrimination, but of positional isomers, which is much more challenging given how similar the spectra of these compounds are. So with these FIBFs, I'm showing here the ortho, meta, para isomers. And the first thing that we did was a comparison of these isomers to a library. For this slide here, I'm just showing comparison to the NIS17 library. And for each of these comparisons, we had 5 replicates of each isomer, and we compared each individual replicate to the library. So the top library match here is showing a summary of the top library match for those 5 replicates. So for example, the OFIBF isomer, when all 5 replicates were compared to the NIS17 library, the top library match was always PFBF. So it was the fluorobutyryl rather than the fluoroisobutyryl isomer. And the match factor ranged from 81 to 90 for those 5 replicates. For the meta FIBF isomer, I think 4 of the replicates returned PFBF as the top library match, and 1 replicate returned OFBF. But again, the fluorobutyryl isomer, or the fluorobutyryl fentanyl rather than the fluoroisobutyryl. But the match factor here was a lot lower, ranging from 62 to 83 for these 5 replicates. And then for the PFIBF isomer, 4 of the replicates returned FIBF as the top hit, and 1 replicate returned para-FBF, again the fluorobutyryl fentanyl, with a higher match factor of 90 to 93. Now, one thing I should point out here, this NIS17 library, I believe it only had FIBF present, and it's the para form, or the para isomer. So it doesn't have ortho and meta FIBF present. So in terms of comparisons of the O and M isomers, the library is just returning the most similar spectrum, which is the fluorobutyryl rather than the fluoroisobutyryl. But that's maybe one of the limitations of the library is, you know, if the correct compound is not present, then it's going to match to the next most similar spectrum. So looking at spectral intensity for these positional isomers, for this concentration study, we again prepared the isomers at 1.5 and 0.1 mg per mil. We collected the spectra, did the comparisons to evaluate how the discrimination is affected as that spectral intensity decreases. So first of all, for ortho FIBF to the other 3 isomers, at 1 mg per mil, we have association of ortho and ortho as we might expect. And then ortho to meta, we have 7 discriminating ions, and ortho to para, we have 2 discriminating ions. So we have discrimination of the positional isomers at the 1 mg per mil concentration, and the number of ions responsible for that discrimination is definitely lower than we saw for the synthetic cathinones, but the reason for that is just the higher spectral similarity of the positional isomers compared to structural isomers, as was shown with the synthetic cathinones. As we reduce the concentration to 0.5 mg per mil, we have association again of ortho and ortho, and we still have discrimination of ortho from meta and para, but again, fewer ions responsible for discrimination with that lower spectral intensity. Now, when we get to 0.1 mg per mil, we actually, we still have association of ortho to ortho, but we lose the ability to discriminate ortho from meta and ortho from para. So this is another issue with spectral intensity, that lower intensity, the spectra are not as representative of the compound of interest. And so again, a recommendation would be that in comparing spectra, the intensities should be similar between the 2 spectra and sufficient intensity to be representative of the compound of interest. So for the FIBF isomers, these data that I'm showing here were actually collected in 2019 on an instrument in the mass spectrometry core on campus at MSU. And this was one of our first looks at positional isomers. So we did collect these spectra over 3 consecutive months, and we did the comparisons. So looking at the table here in the top left corner, this is comparison of OFIBF to the other isomers across the 3 months of collection. So for ortho to ortho, we have association across all 3 months, and we have discrimination of ortho from meta and ortho from para. 13 discriminating ions down to 3 discriminating ions. Looking at meta to the other isomers, we have association of meta to meta across the 3 months. And for the most part, we have discrimination from meta and ortho. Meta and para becomes more difficult. These are more similar spectrally. You can see that we do have discrimination in months 1 and 2, but only 1 and 2 ions responsible for discrimination. And then in month 3, we actually had a false association. But again, this is a low number of discriminating ions in the first place and lower spectral intensity and spectra that are structurally extremely similar. And then the bottom table here shows comparisons of para to the other isomers. So we have discrimination of para from ortho and para from meta across all 3 months. And for para to para, we actually had a case of false discrimination in the first month. And this was similar to the situation that I talked about for the synthetic cathinones, that when we were looking at the spectra, the ion here responsible for discrimination was only present in 1 of the 6 spectra that were being compared. I believe the ion was mass to charge 366, and that was an ion that we never saw again as a discriminating ion. So certainly not a reliable ion for discrimination, but in this particular collection, it was identified as a discriminating ion. But then for para, compared to other spectra of the para isomer, in the 2nd and 3rd month, we had 0 discriminating ions. And the spectrum down in the bottom right here is just highlighting some of the ions that were identified as discriminating ions across this data collection. And again, just to highlight that while some of the ions, for example, mass to charge 71 and 164, are dominant, they're intense ions in the spectrum, there are other ions that were discriminating ions, such as 234, that are very low intensity ions. And so when you're doing a visual comparison of these spectra, your eye is not naturally drawn to those lower intensity ions, but these are still important for discrimination. So those data that I presented on the previous slide were all from a collection in 2019. In 2022, we purchased more of these FIBF isomers. We prepared them and then we analysed them on the instrument in our lab. So another instrument analysing these samples maybe 3 or 4 years after the initial collection. And then we looked at the discriminating ions between the 2 instruments to come up with this list of reliable ions for discrimination. So this again is reliable ions for the discrimination of these positional isomers over time and on 2 different instruments. So we are able to discriminate these positional isomers. You will notice that for ortho and para, meta and para, there is only 1 ion responsible for the discrimination. Again, it's a reliable ion, and it's not unexpected that we have fewer ions for discrimination, given how similar these spectra of these positional isomers are. So in summary, hopefully I've been able to demonstrate a method by which you can compare 2 mass spectra, and we've been able to demonstrate successful association and discrimination of structurally similar compounds, including positional isomers. With this method, we've demonstrated identification of reliable ions over time and on different instruments. And these are ions that we can now consider reliable to distinguish within these sets of structural and positional isomers. And in moving forward, the method does provide an objective way to compare 2 spectra, so a sample spectrum and a reference spectrum, moving away from visual comparisons and increasing confidence in any identifications that are being made based on these spectral comparisons. And then just to finish, I would like to acknowledge a number of past and present students who have worked on this project over the years. Dr. Melissa Willard was a student who developed this method. And then Dr. Hannah Claus was one of the students who started really looking at the application of the method to positional isomers. And then our current students, Andrew Saka and Isaac Willis, have really contributed to expanding application of this method, looking at spectra collected over time on different instruments and for different sets of compounds. Again, I want to acknowledge National Institute of Justice for funding this work and the Forensic Technology Centre of Excellence for inviting us here to present our work today. And I'm going to put this slide up here, and with that, I'd be happy to answer any questions that anyone might have.
All right, hello everyone. I'm Catherine Bollinger at RTI International, and I'll be your moderator for today's Q&A. Thank you, Dr. Smith, for providing such informative presentation. And we also have Victoria here with us joining for the Q&A. So our first question from our audience is, so have there been any projects so far to automate moving the tabulated spectra to the spreadsheet? So that's one of our questions. And then one that kind of relates with this one as well is, do you plan on releasing this as a usable tool like other statistical calculators such as Swig Drug?
So to answer the first question, we have not automated the method to export the data from the mass spectrals or the instrument software to the Excel spreadsheet. One of the reasons that we haven't done that is, you know, everyone might have different instruments, different softwares, and so on, and the functionality to export the data might be different for these different software packages. In terms of a usable tool, absolutely, that is the goal. And I always say that before I retire, I hope that this is a usable tool. We are still in the developmental stages, and part of the development is obviously demonstrating the application, and then, you know, with the work that we're currently doing, robustness and ruggedness, are there improvements that we can make on our end? Can we streamline it, and so on? Our next goal is to work with labs to get more access to case sample data. We did some of this very early on. We worked with the Northeastern Illinois Regional Crime Lab, and they gave us access to their spectra of amphetamine-type stimulants. And that was an opportunity for us to make sure that the method would be applicable to the type of data that a forensic lab was generating. So that particular lab, they gave us access to the reference standards and their case samples that they had previously analysed. And so they had analysed them using their normal operating procedure. They made no modifications to their sample preparation, no modifications to the instrument method or anything. That was just their normal procedure. We got access to the spectra from that, and were able to do the comparisons and so on. So now that we've further developed the method a little bit more, then the next step is to do more of that type of work and have access to case sample data that, again, we can demonstrate that it still works on that. And then the next step would be to offer this as a tool to labs to do some beta testing for us, because there might be some challenges that the labs are facing that we're not thinking about in our research lab, and to have the opportunity to work with labs to be able to start navigating some of those problems are definitely the next steps that we're working toward. Vicky, do you have anything to add to that?
No, just wanted to add that another one of our collaborative works with forensic laboratories was with Jack Hurd up in Alaska, where he had collected spectra and actually GCMS information from 441 different species of salvia. And we analyzed the data there to try and compare them to salvinorins A through D. And we found that in all 441 of those GCMS chromatograms and spectra, salvia divinorum was the only one containing the salvinorins. But we were able to find other molecules very closely related. So data from forensic laboratories are usually collected under conditions that are suitable for such a sensitive statistical technique, just because the forensic laboratories themselves are required to be so precise and accurate in their measurements.
Great. Thank you, Dr. Smith. I think during your conversation with this one, you answered a couple of other questions with your future work, whether you're going into casework samples, that it's not actually implemented in casework samples. Is that correct?
So not yet. As I say, the amphetamine type stimulants data, that was actual case samples that lab had already analysed. They had identified what was present in it, and we were looking at particularly differentiation of methamphetamine and phentermine. Could we statistically discriminate those spectra? And we could. But yeah, as I say, the next step is working toward, or working with labs where we will actually apply it to case sample data just to have a broader sense and make sure that the method still holds up, which I'm sure it will, because we've already kind of demonstrated it does with the amphetamine type stimulants and the salvias.
Great. Thank you for that. We're going to go in and talk a little bit on the statistical method of this. We had one question about with this being done in triplicate, would the math still work for a single sample analysis? So if you are doing a single GCMS sample from a bulk powder compared against a reference or library spectrum, would
We do have versions of the spreadsheet where you can compare one spectrum to, you know, triplicates of a reference and so on. So we do have that. Just the examples that I showed here were based on triplicate spectra. So we have different versions of the spreadsheet set up based on the number of replicates that you might have available.
Great. Thank you, Dr. Smith.
Sure. And just to make a comment on that, we're using the 3x3, three samples, 3 references, because of the real challenge with positional isomers. Easier cases are very simple to do with just one spectrum of each, and they can be done reliably in that way.
Okay, so we have another question on statistical significance and a few on discriminating ions. So the first question is, why is the focus on discriminating ions rather than the statistical significance of a t-test? And that's a 2-part question, so that's the first part of this one.
Can you repeat the question for me, please? Why?
Yes. Why is the focus on discriminating ions rather than the statistical significance of the t-test?
So maybe that's the way that I presented the work. So for each of these ions that we are identifying as a discriminating ion, it's more just to be able to say that statistically, with the t-test that we're doing at this confidence level, that is a significant difference in intensity. And in the presentation, I was just highlighting, you know, when you have these structurally similar compounds, these are the specific ions for which we have that discrimination. I'm not sure if that answers the question. I mean, the discriminating ions are based on the statistical significance of the t-test.
Okay. And so the next part of that may help a little bit.
Okay.
It said, how are the discriminating ions used moving forward? And the t-test was a...
Okay. So, I mean, for our interest here was, you know, you've got structural or positional isomers. They're highly, highly similar, and a visual assessment, you know, you can look and say, okay, that ion is maybe slightly higher intensity than this one, but maybe that's all you can say. Here, we're able to say statistically, yeah, if you've got these 2 spectra and you perform the t-test, we're now saying that t-test is indicating that the difference in intensity of these 2 ions is statistically significantly different between these 2 spectra, and that means you've got a significant difference in your spectra, so these 2 spectra represent different compounds. I'm not sure if I'm answering the question, to be honest.
If there's any follow-up questions, if we ever ask this, go ahead and put those in the Q&A while we have these.
And our email addresses are on the slide here that I think everyone can see. So if I am answering the question, feel free to reach out, and I'm more than happy, and Vicky's the same, more than happy to talk to anyone in more detail about the statistics, because I'm not sure that I am really answering that question, to be honest.
Okay, thank you, Dr. Smith. So do you have a list of reliable discriminating ions? That was one of the questions asking about a list of reliable discriminating ions that you found.
So we do, for each set of compounds that we're working with, we do have reliable ions, but I think for us, that's just more as we're evaluating the robustness of the method. Does this stand up over time? If we're saying that this is a reliable ion for this one comparison, do we see that in all other comparisons that we do? But in a lab, it might be the case that you have your sample spectrum and your reference spectrum, and you're doing that comparison. You can statistically compare these, and you can say yes or no, these spectra are statistically distinguishable or indistinguishable. You might not be too interested in, you know, this ion is always different for these compounds. It really depends on the 2 spectra that you are comparing.
Okay. So there's a question about if there are plans to start looking at some of the nitazene compounds.
Eventually, or maybe not eventually, soon, we are working on the it's one of these things. We started working with fentanyl because at the time fentanyl was the big thing, and obviously you've got all the positional isomers, and now we have other classes of compounds that are becoming more and more commonly seen. So definitely, we will probably look to get a set of nitazenes and start looking at those as well.
All right. Thank you. So our next few questions are a little bit about the application of the method. One attendee asked if the method could be applied to mixtures. So, and then the other one, it's related to the application, is could it help with source identification?
So in terms of mixtures, some of the spectra that I showed and we've done comparisons of, that was actually within a mixture. So as long as you've got chromatographic separation of the compounds in the mixture and you're collecting the spectrum of the individual compound, yes, it can be applied to mixtures. In terms of source identification, I'm thinking that question is more related to like synthesis methods or something. And yeah, you could apply it if you had a complex mixture. Maybe you've got, for example, a precursor that you're not sure what the identity is. You could compare the spectrum of that precursor to a reference or the library to confirm the identity of that precursor. So you could potentially use it in that manner to look at source identification.
Okay, thank you. We just we have another question that just came in. It's about the spreadsheet. So for the yes, no question of statistically significant difference within the summary box, is that final comparison of the two spectra a no if there's only one discriminating ion, or does it depend on the ion being reliable?
So if there's one ion for which the null hypothesis is not accepted, then those two spectra can be considered statistically distinguishable. And what we see for some of the positional isomers, so meta and para, specifically FIBF, there's one ion, mass to charge 234, responsible for that discrimination. Even though it's only one ion, it's statistically significantly different in intensity, and therefore it is. So the number of discriminating ions doesn't matter. One ion is sufficient to be able to statistically distinguish these spectra.
Okay. Thank you. All right. So our next question is just asking about if they could use this method on data that they've collected in their lab.
Hopefully. Yes. So yeah, again, some of the things that we are realizing as we're doing these comparisons is, for accurate comparisons, you've got to have sufficient spectral intensity. Ideally, for the two spectra that you're comparing, they are similar intensity, and the spectrum is sufficiently representative of the compound of interest, especially, your reference spectrum. So, these are things that we're learning as we're doing this. So as long as your data fulfill those criteria, yeah, I mean, the method should be applied or should be able to be applied in your lab.
Great. Thank you, Dr. Smith. And we have, okay, two more that's, so one of them asked, so what are the limitations of this? And I think this is related to maybe what you were just talking about, because it just came in. So it's asking about limitations.
So again, spectral intensity, very low intensity spectra or spectra that you're comparing for which there is a large difference in intensity. Vicky, feel free to jump in here while I am thinking about this.
You mentioned that the compounds need to be chromatographically resolved from each other. So overlap of peaks, overlap of different chemicals within the sample is a very serious problem. So very rapid separations, rapid ramps in temperature, for example, you want to be sure that there's adequate separation of the substances in the sample.
Yep, good point. Yep.
Background noise is an issue. So a well-maintained and clean system is important.
Yep.
Okay. Another question came in about the gas type. So have all the instruments you've been using been helium instruments? And do you foresee any issues with instruments that are using hydrogen?
So one thing that I didn't touch on, in our spreadsheet, we have a list of common contaminant ions that we do not include in the comparison. So for example, your background ions. So depending on a hydrogen system, if there were any additional known contaminants, anything like that, then we could modify the spreadsheet to accommodate that. But for the most part, I don't envision any differences. Again, it really comes down to maybe the answer to the last question, a well-maintained instrument, little background noise, good signal intensity. Those are the kind of chromatographic and mass spectral features that are the most important for accurate comparisons. I don't foresee hydrogen being or making or having any issues that maybe some modification to the spreadsheet in terms of those background or contaminant ions. But apart from that, I don't envision there would be huge problems with a hydrogen-based system.
But that does bring up an interesting point. We've used the DB1 and the DB5 columns for most of our work. So the background ions that we know that we have to be careful about are ones that are specific to the bleed from those stationary phases. And so if you're using a different stationary phase with different bleed characteristics, we would want to look carefully at what those ions are. What we've done within the program is that if the variation in those is less than 5% of the base peak, we ignore it. But if it's more than 5%, then that's likely to be an important ion in the compound, not just bleed from the column. And so then it's included within the statistical comparison. But that would need to be inspected for a different chromatographic column.
All right. Well, thank you for our presentation today. It's been very informative and a great conversation with all of the questions asked today. If you have any other questions that were not answered or you need further explanation from our experts here, their email address are on the screen. And thank you all for attending our presentation today. Thank you.
Thank you very much.
Thank you.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.